Okay, now back to the outline, and this is the third section of the synthetic aperture radar lecture. The first two sections were on the introduction, first two pieces of video, and now we're going to look at the basics of synthetic aperture radar. And you can see we've broken it up into approximately 8 pieces. We're going to look at the airborne geometry, or it could be the spaceborne geometry of a synthetic aperture radar. We're going to look at cross-range accuracy limits under real aperture radar conditions, and then two types of synthetic aperture radar modes, an unfocused mode and the focused mode, which is pretty much always used now that we've got plenty of digital processing and that sort of thing. That was used. This unfocused was used earlier. We'll look at the interaction of range and Doppler velocity, range gate traveling of the target, PRF limitations, and what they'll be caused by and how we have to live within them to set the PRF. We'll look at the range Doppler ambiguities, the limits to the swath size that we can scan over, and signal processing evolution. Okay, now let's start off. The first thing we start off with is the geometry. And I'd advise you to print out from the PDFs this picture if you're looking at the video, at least this one view graph, because there are going to be a lot of different these equations, and I'll use the words and the symbols, but this is the definition of all the symbols for each of these different entities in the geometry. Here we have, in this case, an aircraft, could be a satellite. We've got the synthetic aperture marked off. The length of the synthetic aperture will be capital L sub SA. The real antenna aperture along the track antenna length is D. Here's the depression angle. There's the slant range to the center of the beam on the ground. Here's the cross range and the long range dimension of that beam that's on the ground. But this is the cross range of the entire beam. We're going to get much better resolution in the cross range when we process the data with synthetic aperture. This will be the ground range to the target, the real antenna beam width, the altitude, slant range, depression angle, which is pi over 2 times the angle with respect to the vertical, or the angle of the beam with respect to the vertical. And you can see all these different parameters as we go on and we derive what are the different resolutions and dimensions that the system will be constrained by and have. Now for the cross-range resolution, we have limits. We've gone over a little bit the real aperture. We'll recapitulate that for a moment, and then we'll look at synthetic aperture processing. And there are two kinds of processing, one unfocused mode and one the focused mode. And I note the unfocused mode because historically, back 10 years ago, people built many radars in the unfocused mode. Right now, they pretty much all use the focused mode. But so if you see in the literature or a system that, and I refer to it later, I show you some of the first synthetic apertures data from space or something, you'll say, oh, that's an unfocused radar. You'll know what it means and how the limits are on the resolution for each of these. Now for the cross-range resolution limit for a real aperture, I'll go through this pretty quickly because we've really done it. Here we see an aircraft along a path. And here's the slant range, the beam width, and the beam width is just lambda over D, where D is the real antenna aperture. And the cross-range resolution for a real aperture antenna is just the beam width times the range, the slant range, and that's just lambda R over D. And for X-band at 3 centimeters, and a size of an antenna of 3 meters, which would be a good size for an aircraft, the cross-range resolution at a range of 100 kilometers would be 1 kilometer. That's huge relative to the range resolution that one can get. And this is far and away easy to obtain good range resolution if you take 10% of the bandwidth. in a radar. And synthetic aperture radar allows measurement of high cross-range resolution by using the aircraft's motion to generate a long antenna aperture, sequentially rather than simultaneously as in this above example. Now, looking on to cross-range resolution limits with an unfocused SAR, I want to point out this fact that here's an aircraft, and at each of these different points, these are where we transmit. Okay? And this is our aperture, our synthetic aperture size. And they're the element points along the flight path where the synthetic aperture radar transmits and receives pulses from each and every one of these to a target located down here. Now at the center, where the angle between the flight path and the distance to the target are perpendicular, you're going to have the shortest distance, r. But when you get up to the point where you're along the flight path and the distance is lambda over 8 plus that range, you're going to have focusing problems. And if you don't do something to take care of those focusing problems, then the radar is called unfocused. And the cross-range resolution is twice the square root of the distance times lambda. And this can be corrected, and we'll look back. The factor of 2 appears in the cross-range resolution, again, because we've got the two-way path, because of the conventional SAR has a two-way path, and the conventional antenna only has one. And unfocused radar SARs aren't used because of the digital refocusing is so simple to implement, and it was very difficult to do it otherwise. Now, but what thing I want to point out is that if you transmit out and back, you're going to have a different phase than out here of the return signal if you come out and back. So we're going to have to do that correction and go to a focused SAR. And the phase term that we want to add is going to be this phase term. And this limit in resolution is because we're operating in the far field, and it's fixed by adding a phase term to each received signal, correcting for the spherical nature or in the Fresnel region of the wavefront. And here is the phase term that's added, and these have all been defined. And y is the distance from the element to be corrected away from the center of the synthetic aperture path, that minimum r. Okay, so we have to add a phase term, and the correction is different for each range, and the angular resolution after this correction is the same as that in the far field. So that helps us with our resolution. Here's again another view of the same geometry really as the applied before with different emphasis, and the parameters are all the same as in the previous. And this is the case, one of a satellite traveling overhead. Here's the synthetic aperture length from T1 to T2. Here's nadir, we're pointing down. And it defines the angles, and here's the synthetic aperture length from here to here. And from here to here. And the synthetic aperture length is the beam width times the range, and it is that quantity. And then the integration time that we have is the synthetic aperture length divided by the velocity of the aircraft. And that's just this quantity. And so when we combine them, we see that the cross-range resolution that we get just comes to d over 2. Which is just the size of the antenna. D is the along track antenna length, which I defined in the earlier view graph, and it's a small size of the antenna along the track of the satellite or the aircraft, and it says that the range resolution in the focused mode just comes out to be d over 2. It's only a function of the size of the antenna length. Okay, when you look at all the geometry. Now this is the new aperture, L. This is the synthetic aperture, lambda r over d, and the cross-range resolution of the focus SAR is just lambda r over twice the synthetic aperture. Here's the lambda over d and the range, and then we've got the factor of 2 because it's a synthetic aperture system, and when we all cancel out, we get the d over 2. So that's a derivation of how it comes out to be d over 2, which I stated in the previous view graph. So notice that the resolution of a focus SAR is independent of the range and the wavelength, and is solely dependent on the dimension of the dimension d, that length of the antenna along the path of the real antenna. Okay. Now, of course, you can have an awful lot of other things mess things up. You can have the aircraft in turbulent weather, and that'll interfere with the phase. The corrections you do can be imperfect, and that will make the resolution less. But in an idealized system, it's independent of d over 2. And we'll get into a little bit later those other factors. Another attribute of synthetic aperture radars is that the beam widths are different than for conventional antennas. The factor of 2 in the beam width, I mentioned 2 slides before, and the cross-range resolution is because of the difference between the two-way path and the one-way path, and two-way path in SAR and one-way path in conventional antenna. And you can see these are the patterns with uniform weighting. For a SAR, you see these factors of 2, and for a conventional antenna, here is the pattern. Okay, now when we take these data and we plot the cross-range resolution for a 3 centimeter X-band, 3 meter dish antenna, if we have a real aperture and we're at 1 kilometer, we'll have a resolution of 10 meters. If we're at 10 kilometers, 100 meters. These are log scales, notice. And a range of 100 kilometers, we're way up there at a kilometer cross-range resolution. But when we go to an unfocused SAR, where we have twice the square root of the range times lambda, we get not a kilometer, but we're down to 110 meters. But we get down to, for a 3, if d is 3 meters, the size of our antenna aperture, we'll have a 1.5 meter resolution at 100 kilometers. And that's where focused SARs really, they get their juice from. Now we're going to look at constraints on the resolution because of range ambiguity. We want to avoid antenna grading lobes and the influence of the grazing angle on these issues. As we said earlier, the PRF in the system, it's got to be low enough so that range measurements are unambiguous, and we want it high enough so that the grading lobes won't fold over and give us problems when the spacing of the elements is too large. We want the PRF high enough to avoid angle ambiguities. And so thus the swath size and resolution cannot be independently chosen in a synthetic aperture radar. And now we're going to derive so to avoid antenna grading lobes, for the synthetic aperture, the position of the first grading lobe should be located at the first null of the element pattern of the real antenna. And the synthetic aperture's first maximum position, the angle is lambda over twice the spacing between the elements in the synthetic aperture with a factor of 2. And this is just the PRF divided by the velocity of the aircraft. noted down here. So that first null is approximately lambda over capital D, and the first maximum is here. And the theta G, the first grating lobe maximum of the synthetic aperture, has to be greater than the first null of the real antenna. And when you combine these factors together, it says that the PRF has to be greater than twice the velocity divided by that length D of the width of the antenna, which is really the velocity divided by the cross-range resolution, the D over 2. Okay? So that's one limit on the PRF. The PRF's got to be greater than that amount. Now, we also have to, in the avoidance of grating lobes, we have to have the PRF less than twice just move the PRF over. This is an equation constraining the unambiguous range. So it follows that from this is for the grating lobes, and this is the constraint from the unambiguous range. It follows that this factor has to take place. So it says that when we feed in the condition here, that if we assume uniformly illuminated antenna patterns and other idealized that were assumed, the PRF constraint becomes this, and the unambiguous range divided by the resolution is less than C over 4.7 times V. And essentially the same results you get if you have a cosine illumination weighting on the antenna system. So this is where the PRF has to fall between these limits. Now, the influence of the grazing angle has on the swath size, the swath that we look at, that we scan the beam over. And the swath width is often much smaller than the maximum range of the rate. In addition, the beam projected onto the ground is impacted by the grazing angle of the beam, also reducing the need for a maximum unambiguous range. And these factors impact the previously derived constraint equations, so that this equation we got on the last view graph becomes this, where phi is the grazing angle that we're hitting the ground with, and was defined earlier. And this S is the swath width that we're looking at, and this is, of course, the resolution in the cross range. Okay, now let's spend some time. I've just gone through a lot of equations, and let's take a real example of a system. It's really going over a problem, and the problems I've assigned are similar to this, but I wanted to go over one with you to give you a chance. Say we've got a synthetic aperture radar, and it's operating at C-band, 5.5 gigahertz, and it's got a pulse bandwidth of 500 megahertz. It's satellite based, that it's at an altitude of 565 kilometers, and it's moving at a velocity in this direction of 7 kilometers a second. And the SAR antenna has dimensions of 5.2 meters along the track by 1.1 meter in height. The antenna is oriented such that the antenna beam bore sight, that's the center of the beam, and the ground are at an angle of 40 degrees. So that angle right in there is 40 degrees. And one's going to need to use geometry, and as it's defined very carefully in that earlier, you got to do your geometry to get the right angles from the depression angles. Okay, now let's find the size of the antenna footprint in cross range and along range. The swath size along the radar range track and the swath size in cross range are just here. And D is the antenna size parallel to the altitude vector, up and down, and the H is the antenna size parallel to the velocity vector of the SAR. Okay? and here's the slant range. The long range footprint size is just this quantity. And what I'm going to do, I'm not going to go through these numbers exactly, but I want you to go back to the geometry after the lecture, after you do the lecture, and prove that these things are correct. So I'm not going to, I'm not going to treat you like sixth graders, You're all supposed to be advanced students, at least, very advanced undergraduates or first-year graduate students, and show that this is the equation from what we've derived for the long-range footprint size, and you get 48.2 kilometers. And the cross-range footprint size is this, and comes out to be 7.8 kilometers. Okay. Now, what's the distance from the center of the radar beam footprint to the satellite ground track? That range to the footprint center is just the h times tangent of phi. I want you to go back and see that it really is by looking at the geometry. And that comes out to be approximately 475 kilometers. And now we want to look at the, assume the radar size that we've talked about. What is the range resolution and cross-range resolution for the real aperture antenna? Okay, now in the range dimension, it's just delta r divided by the sine of phi, because we've got the grazing angle issue coming into play, and delta r is just c over twice the beam bandwidth. Here are the quantities, and you get 0.482 meters, and the cross-range resolution is just the same as the footprint size, because we haven't done any synthetic aperture processing. It's the same as the 7.8 kilometers we got in the previous slide. Now, when using the synthetic aperture mode, what's the minimum PRF to avoid grating lobes? The minimum PRF to avoid grating lobes is just this quantity. I want you to go through the algebra to see that. And go back to those derivations a couple of view graphs before. And what is the maximum PRF that will achieve a reasonable unambiguous range? And the maximum one is the range is measured unambiguously. Here we are, and that comes up to be the 48.2 kilometers, and the maximum PRF is 7.3 kilohertz, and that RU is just the maximum footprint size that we can have here. Okay, for the PRF, if I pick one between that 2 and the 7 or 5 kilohertz, how far does the satellite move in 1 PRF? Because we want to make sure that the target's within the beam width. Okay? And we don't have grating lobe problems. And we're moving at 7 kilometers a second. Time between pulses is 0.2 milliseconds. The distance moved is 1.4 meters. The element spacing is 25. So grating lobes are an issue. The first grating lobe is at the inverse sine of that quantity. Got to go back again and check that out. It's at 1.6 degrees. And since the element beam width is 0.61, essentially 0.6 degrees, grating lobes are not a problem. And so this is the constraint we have. There's no problem with grating lobes. Okay? Since this quantity is greater than that, there's no problem with grating lobes. Now 7. Say the returns are processed for 0.8 seconds. The satellite goes to 0.8 seconds. With focusing computations, what's the length of the synthetic aperture? Well, the number of pulses processed is just the processing time times the PRF. And we're going to be processing 4,000 pulses in that 0.8 seconds. And the synthetic aperture length is just that 0.8 seconds times the velocity. So the synthetic aperture length is going to be 5.6 kilometers. And is this length consistent with keeping a point within the beam footprint for the computation? And the answer is yes. The cross-range footprint earlier was calculated to be 7.8 kilometers, so the data will be processed within the footprint of the beam because the synthetic aperture length, the amount that the antenna that the beam will traverse is 5.6 kilometers, and that's less than the footprint size. Okay? And then last two questions is when the system is operated as per 6 through 8, what are the achieved long range and cross range resolutions? And a long range, we get 0.482, and that's the same as in section 4, problem 4, I guess you'd say, part A. And we have here that the cross-range resolution is just here. And we don't put in D over 2 because we could have the 5.2 meter antenna length of the real aperture is the best resolution you can get. And we have only processed the data for 0.8 seconds. So we didn't process as much as we theoretically could have to get better resolution. So you want to put in here the synthetic aperture length to find out our actual cross-range resolution for this radar configuration operating in this mode. We have for 0.8 seconds. Yeah, that limited the synthetic aperture length. And we get 3.6 approximately meters. And how does this compare with the theoretical best resolution? The long-range resolution, same as calculated earlier. The cross-range resolution, 3.62, is not quite as good as our theoretical best because we didn't integrate along the flight path as long as was possible while still keeping the target spot in the beam as the radar moved. Okay, now we'll take a break here, and then we'll go on to the next section.